Hello and welcome back to the Raw Code Academy. In this video, we're following on from our installation and overview guide of Tetragon, an eBPF security and observability tool for your Kubernetes cluster. In this video, we're going to go a little bit deeper than the installation and a general overview. And we're going to look at one of the main use cases for adopting Tetragon within your clusters. And that is runtime enforcement and observability of file access across your container workloads and the host they run on. So, let's get into the docs and have some fun. Alright, here we are at the Tetragon documentation, or at least we will be now. Now, there's a few things I want to cover before we get to the use cases, and the documentation itself well covers file name access and what we can do. But there is a little bit of vocabulary that you have to be comfortable with and a few concepts that you need to know before you should really start writing tracing policies. Fortunately, the documentation has this pretty well covered too. So if we go to concepts, tracing policy, we can now begin to dive in to what a tracing policy is composed of. So the first thing that every tracing policy needs is a hook point. A hook point can be one of three things. First, a K-probe. This is a kernel probe that allows you to hook in to functions called within the kernel. Second, we have U-probes. These are user probes, go figure. And these allow you to hook in to any function called within a user land binary. And lastly, we have trace points. These are more generalized points within the kernel that you can hook into that are stable across kernel versions. Like the documentation says, going from kernel version to kernel version, K-probes are not guaranteed to be consistent. But trace points are. And we'll take a look at each of these as we explore how to do file access, observability, and runtime enforcement. And we're going to kick things off with the K-probe. Okay, so let's write our first tracing policy using a K-probe. Now, when you're working with a new Kubernetes resource, usually helps to find some examples online or just use kubectl explain, followed by the name of your resource. Here, a tracing policy. It tells you that we need an API version, kind, metadata, and spec, but of course, you already knew that. But at the top, we do get the group, the kind, and the version that we need to successfully write the start of our manifest. So let's do API version, Cilium.io, v1, alpha 1, kind, tracing, policy. Like everything, we need a metadata with a name. I'm not fussed what that is. We leave it like so, and then we need something. So let's jump back and do kubectl explain again, only this time we'll add spec. And we can see all of the properties that our spec can take. And we're curious about K-probes, so we'll expand that like so. Now we can see that this is a list of K-probes with an args, a call, return arg, action, selectors, and syscall. So let's start to fill this out. We know that we have K-probes. We know it's a list. It needs some sort of call. Well, the call is the name of a function to apply the K-probe spec to. This just means the name of the kernel function or syscall that you want to monitor. Now, we're doing file access stuff today, so we're going to take a look at syswrite. And this is a syscall. So we're going to mark this as syscall true. We know this because we can see here that we can specify a boolean to indicate whether this is a function or a syscall, with the syscall being true. Now, unfortunately, this is not enough for us to start tracking and observing this syscall with Tetragon. We have to provide the args, which is a list. Let's jump back to the terminal. And we can see the args here needs index and it needs type. These are the two required properties that we need. And this has to describe the function signature for the kernel function or syscall that you want to observe. Now, assuming you probably haven't memorized this stuff, you can look it up on the man page if you want, or it is available on any good man page website like die.net. And here we can see the function signature for the write syscall. So let's just paste that here for now and work this out. So when we did kubecontrol explain, it said that we need an index and a type. The index just maps through the arity of the function signature, meaning we have an index 1 and of course 0, and index 2 because we have 0, 1, and 2 properties or fields on this function signature. Now, the type for the first property is int because we have an int. The type on the second is charbuff. Now, the C programming language doesn't really have any concept of strings. It has arrays of bytes, characters. When we see this, we do need to provide a little bit of extra details so that it understands the size of that property, which is where size args index comes in. This is the index of the count, the size t. And index 2 is of type size t, like so. And now we have enough of a tracing policy, which I don't know why I called trace points. Let's call this right. In fact, it's not this right, underscore right. So let's fix that while we're at it. And we'll even rename the file just because these things will bug me. Like so. Now we have a tracing policy that will tell us every time the syswrite, the syscall called write, is executed within our kernel. So let's check. So we jump over to our terminal. And we're going to do apply on that syswrite file where I got a property name wrong. Let's do the explain again. Size arg index, extra s, and apply. And of course, resource names DNS compatible. Voila. All right, so now we have a tracing policy. Wonderful. So the next thing we want to do is start pulling out all of the logs on our Tetragon pods so that we can see the feedback, observe the syscalls within our cluster. So if we do a kubecontrol kubesystem get pods, you'll see that this is a 3-node cluster because we have a daemon set for Tetragon, which has 3 different pods. So we're going to get the logs for everything so that we don't have to chase the logs that we're looking for. And to do that, we'll just do a kube system logs -f label app.kubernetes.io instance equals Tetragon. Now, if you remember from the first video, by default, Tetragon will show you all the process enter and exits. So we're just going to skip past that so that we can start to filter on the logs that we care about. So I'm going to split this pane and we're going to apply my sleepy YAML. A sleepy YAML just runs Ubuntu with a sleep infinity, but it does mean that we can exec into Ubuntu and run bash. So as you can see, even by just execing into this container, our logs are already filling up again. So let's just clear that up. And now we're going to run echo hello, and let's write that to this file here. And we can actually see already we're seeing our process kprobe here for syswrite emitting events already. Because of course, not all writes happen against the file system. So let's write that file. Now we executed a write, but there's so much going on. We're actually getting a lot more writes than we can fully understand. And it's actually going to be rather difficult to find and pinpoint the one event that we want, because let's jump back to here. When the write syscall is called, first, it writes to a file descriptor rather than a file name. So we're not even going to be able to see that we wrote to something called DEF because at the syscall level, there's no such thing. What we can see, and why don't we just grab one of these and throw it into a buffer. And we'll save this as output.json and let VS Code do some formatting. So we can see here that we have some sort of exec ID. Now this looks like a base 64 encoded string. So whenever you see one of these, we can decode it and we see that this happens on one of our nodes. No surprise. We have the PID, the UID, the current directory, the binary that executed it. And then we get our logs enriched with container and Kubernetes information. And that is pretty sweet. So we can actually see here from Tetragon that this pod was the Ubuntu one in the default namespace with this image that started here. Its PID is here, it has these labels and so forth. So we're already getting a lot more information from what actually happened in this system. And if we scroll down, we can actually see the parent process, which in this case is runc and containerd, that is responsible for executing our workload. Now down here, we have the information that we matched again in our tracing policy. We can see the syscall, which is syswrite. Now, because these are architecture dependent, Tetragon has detected the architecture where the pod is running and prefixed it to get us the right syscall. Thank you, Tetragon. We can see that we are writing to file descriptor 2, and here's our bytes. Again, we have a base 64 encoded string. Whenever you see one of these, decrypt it. And we can actually see that we didn't catch the write that we did with the echo. Instead, we caught the prompt being written to my terminal. We then have the action and the policy name. So we need to add a little bit more information to our policy so that we're not getting bombarded with all of this noise. So let's dive into selectors. Okay, so let's jump back to our terminal. And we'll close down our Ubuntu for now, pull up our explain, and look at kprobes. We can add one more property, which is our selectors. And this allows us to add actions, args, binaries, capabilities, capability changes, namespaces, PIDs, and return args. Now, we're not going to sit and dive through lots more explain commands to understand this. The Tetragon documentation is rather good, so it would be a shame not to use it. Let's jump over here and we can see that we have all of the documentation on the selectors that we can apply to our tracing policy. So in order to look at match args, I've decided to fetch a rather more complete YAML from the Tetragon examples directory. You can find this on github.com/Cilium/Tetragon and then find the examples folder. Now this is a really cool example because it has more kprobes. We're now using kernel functions rather than just syscalls. And it already has selectors across each of these that it's matching against. And we're going to take a look at match args first. So here, we're looking for the security path truncate kernel function. Now, this has one arg and a return arg. But how do you get these? Right? There won't be a man page for every kernel function. Well, that's where SourceGraph comes in if you want to make this a bit easier in your life. You can use SourceGraph to search the entire Linux codebase. We can say type, symbol, and copy the function name. Now we can see the header where this is defined and the function itself. In both counts, we see the return value is an int and it takes some sort of path as its only argument. As such, arg0 is a path and the return value is an int. Now, because this has taken a path, we can filter using match args on the first parameter, the only parameter, and say equals, etc., password. So let's apply this to our cluster and pull up our logs. Let's get rid of all this. And then instead of splitting this vertically, let's just jump over to the side where I also have an Ubuntu bash in this cluster. And let's check our path, etc. password. So let's open Vim and add bash 123. Now if we pop over here, let's grab one of our key probes that we can see, like so. And let's put this into our output.json so that we can format it. We can see here, and if we scroll to the bottom, that our security file permission function was a match for our etc password file. So let's tweak our security file permission selectors. And instead of just filtering on etc password, let's do a prefix for everything inside of the etc directory, like so. We can then come back across here, apply, get our log, clear the screen, and this time we'll write to lsb release. Pretend this is Ubuntu 25. Now we could pop over here and we'll see that we still have a kprobe JSON, like so. Jump back to our JSON and paste. And if we scroll down, it is our security file permission, this time against our etc release. So our prefix is working. Let's take this one step forward and block any write access to this directory. So back on the selector documentation, let's go to match actions. From here, we can do a whole bunch of things, but the first thing I want to show you is sigkill. This just means stop the process. Now, this example is fortunately exactly what we want to do. So let's copy our match action here and go back to VS Code. We come down to the end of our selectors and add our match actions, saying that we want to kill the process rather than letting it succeed. So let's apply this to our cluster, assuming we format it correctly. And get our logs. So let's open password, and it is killed before we even do anything. Perfect. Okay, so the last thing I want to show you is one more action. There's a bunch here that we could work with, but I want to take a look at the get URL because I think it's quite fun. So let's copy this and come back here. Now, instead of killing this, let's use the get URL action, and instead of going to eBPF.io, let's create a box, a request box. This gives me a URL, like so. We'll paste this in, go to the terminal, and apply. All right. Let's pull up our logs, not that we need them really this time. And we delete our swap and we get access to the file because this time we didn't do a kill. So if we come back over to our box and hit refresh, you'll see that we got an HTTP request, multiple in fact, letting us know that somebody tried to open a prefix within that path. Now, a simple GET request in this fashion is not that immediately helpful, but it would allow you to kick off some sort of Slack-driven workflow that posts a message saying that one of your security profiles failed and maybe you want to start looking at your logs. Now, of course, there's other ways to do that, but it's still fun to think about what ifs, And I think the get URL is what if. So that is our look at file access permissions with runtime enforcement using Tetragon. I feel like we've barely scratched the surface. There's so much awesome things that we can do with Tetragon. And as much as this may inspire you to go and play with it, and I definitely encourage you to do so, please remember that security is an onion. It has many layers. You're not going to be able to secure your systems with 30 lines of YAML. You need to layer on various syscalls and functions and remediation patterns in order to fully protect and observe your system with a tool like Tetragon. But the best time to start is now. So get it installed. Start observing special paths within your cluster and then decide how to act. Best of luck. We'll be back for part 3 of this course as we explore process lifecycles. I'll see you then.